Good afternoon, I'm Mike Gilbert with Howard Shockey & Sons. Today we're conducting the owner training for Martin Luther King Middle School. We'll be covering cooling towers, fans, the pump package, and the heat exchange system. And we'll start off with the cooling tower training, and I'm here with Tony from Siemens.
How you doing? We're going to discuss the condenser system at Martin Luther King Middle School. We have two cooling towers that operate as lead lag. They switch on a weekly basis. They can also operate together. If our supply temperature sensor is greater than 78 degrees, that set point is adjustable, then we'll bring on an additional cooling tower. The chiller operates at an optimum condenser temperature between 75 and 80 degrees. And what I've seen is if there's some lag or if there's an issue with the lead tower, we don't want to wait too long to bring on the secondary tower system. So depending upon which unit is operating, we have an isolation valve here to restrict flow to the unit that's not running, and we also have a bypass valve. This valve is normally open to the towers, and then in the case where the tower water is too low coming back into the chiller barrel, we'll open this bypass and bypass the cooling tower section. The pump skid houses all of the main pumps except for the inline pumps, which we'll get into in a little bit. The cooling tower drives are in the far right corner of the plant adjacent to the chillers. They control the cooling tower fans. We control both the start-stop and the speed of each drive. And then we'll have proofs inside of the train drives to pick up current off the motors. We have backnet communication to all these pumps and fan drives, and the pumps on the skid are completely controlled through backnet. There's no hardwired control of those whatsoever. But we do have hardwired controls on the cooling tower fans. The inline pumps, which we have on the heat recovery machine, pump 10, and there's also one not depicted on this drawing for the heat exchanger, pump 9. Those two have hardwired starts, but no speed reference. The only speed inputs that we have are for the cooling tower fans and then our secondary chill water pumps. The other speed references should be coded into the drives and should have been set by the balancer. The only thing we do with those is enable, disable, lead lag, and then monitor alarms. So we have the water coming from the cooling tower, going through whichever pump is selected on the skid, pumping our condenser water, and this just illustrates the barrels of the condenser side of each chiller. Each chiller system has its own isolation valve, so we can manipulate flow through those. If chiller 1 is down, this valve will be closed. As you can see, each valve is also normally closed. It takes power to drive open, or there's a manual lever on the side of those brave valves where you can manipulate the position if necessary. They are 120 volt sourced, and then it takes a 24 volt actuation to make them move. We have a discharge temperature on the other side labeled CRT. This is condenser return, but it's the discharge through the barrel after the chillers warm the water back up. And then we have a differential pressure sensor measuring the DP across the heat exchanger section here. This is a two-way bypass valve. If our energy recovery machine is operating, which if the chiller is operating, it calls for in the sequence to run that machine, then we'll divert some of the water from the cooling tower into that heat recovery machine, allowing the flow switches to make. This will be set by the balancer on whatever flow requirements it takes to make that unit run. We have domestic water coming in through heat exchanger 2. There's a temperature dispersion between condenser and the city water, preheating some of the water before it comes to heat exchanger 3. If the chiller is running and the heat recovery machine is operating, we'll go ahead and enable this pump 10, this circ pump. And all that does is circulate through the condenser side of the heat recovery machine. That will further warm the water from heat exchanger 3, and through this three-way valve V1, we can either supply domestic hot water straight from heat exchanger 3, or in the case of this unit not running or not able to reach 110 degrees from this leaving water set point, then we can take the normally closed position of the valve, drive that open, and then we'll recover boiler water through heat exchanger 4, increasing the domestic water output. So the purpose of the heat exchangers is to both limit the energy use of the cooling towers and drop the condenser water, and preheat the domestic water before it reaches the building. Are there any questions?
Just to point out for anybody that's viewing the DVD that this drawing is in the operation and maintenance manual, it's in the building automated system submittal, and it's the chiller plant detail.
Now we're going to discuss some of the features you'll see on the graphics of this screen. This screenshot is in the submittal and the OEM package, but it also may resemble what you find on the graphics of the operator. In the case of an alarm generated from a pump or cooling tower fan, you would have a red point in place of the text that's black here, and you'll also have an alarm screen at the bottom of the toolbar that would flash, letting the operator know that there's an issue with a piece of equipment. In the case of one of these cooling towers alarming or one of these pumps alarming, the text would be red around the point indication, and you would also see the secondary point energized. Whenever we have an alarm and there's two possible pieces of equipment to run, then we switch over and we'll operate the lag equipment or whatever point is available. When it comes to the bypass valve, I may not have mentioned this earlier, but this bypass valve operates to maintain a reasonable temperature deadband coming back into the chiller. If the condenser water is too cold, it can lead to mechanical failure, and if it's too hot, it can also lead to high limits, alarming the chiller and the chiller shutting down. So we'll bypass the cooling tower if it gets too cool. We also monitor the cooling tower fan speed. If the fan speed is elevated beyond the point where we assume that a high demand for cooling is active, we don't want to shut that valve down. So we will modulate that valve between 0 to 10 volts, going from a normally open position to the cooling towers at 0 volts to a full bypass at 10 volts. The same with this two-way bypass. We don't want to cut our circulation completely off to the cooling tower, nor do we want to isolate just the heat exchanger loop with full flow. So that'll modulate, and we'll have limits in based on the balancer's recommendations. There is no backup for pump 10 or pump 9 that's flowing through heat exchanger 1. So if they do fail, you will have a failure on your heat recovery machine. In that case, you would see both a red text or red box around pump 10, and you would also likely get alarms off the heat recovery device. The heat recovery machine is not necessary for the chillers to run. This has a fairly low set point, and if the domestic water system is up to temperature on the leaving side of heat exchanger 3 or heat exchanger 4, this unit is going to back down and will likely shut off. Right now it's got a set point of 44 degrees on its evaporative coil, which is the condenser loop to chillers 1 and 2. So generally speaking, once the chillers are enabled, the heat recovery starts up, the temperature of the condenser water drops rapidly. The chillers are bypassed at that point, and typically everything sits at minimum until the load resumes on the system. So you will see a fluctuation sometimes between the heat recovery turning off and on, and then your cooling towers with a ramp up or down. Any questions?
I have a question.
Yes, sir.
During heating season,
Yes.
January, February, I assume that our demand for cooling chill water is going to decrease.
Yes, and these,
And our towers will, the BAS will disable the condenser water system.
the towers and the chiller system are not disabled based on outside air temperature. The way the sequence is written, it's energized or de-energized, enabled, disabled on the demand for cooling. With some of the, the drier temperatures that you may see in the heating season, it's not likely to have to dehumidify, but that is part of the sequence of the air handler. So if you do go into a dehumidification sequence, the chillers will be enabled.
So, okay, January, nighttime, those areas that actually have a cooling demand, such as our elevator machinery space and data room, are served by a split AC unit, so that they're not calling for chill water. Is there potential for our basin water to freeze during the winter months?
Well, the cooling towers do have heat trace on the piping.
Right.
I'm not sure if it is, there's basin heaters also. We do monitor the status of the heat trace, however, not the basin heat. So other than this discharge temperature that we have here, we have no way of knowing what the cooling tower basin is doing as far as temperature goes. There are points within the chiller for pump demand. The chiller can tell us if it needs to run a pump without us having to energize the chiller. So in that case, we would turn on the condenser pumps and allow water to flow, open the isolation valves and allow water to flow through the chiller. Typically, it's not going to recognize that temperature requirement because they're inside. If it tends to be an issue, then program could be written, to run maybe an hour every 4 hours. If the outside air temperature is below 38 degrees, we could open the isolation valves and just run the equipment, run the pumps through the cooling tower. But we don't have status on the basin heat.
Okay. Thank you.
All right, well, we have our two Vapco cooling towers, two each individuals, pretty much standalone cooling towers. Like Tony was saying, one can run or the other one can run or both of them can run together. The good thing is one can operate and be drained for maintenance while the drain for the other one is worked on during maintenance. They're designed for ending water at a temperature of 100 degrees, leaving water temperature of 85 max, with a flow rate of 775 GPM in each cell. The air comes in the side right here, as you'll see right here. It's induced draft, comes out the top. The water is fed into the top up here, and it goes through orifice plates, which is basically nothing but a plastic PVC tube. And then the orifice is drained down on each one of them, and they have, I call them mist eliminators that run down through the top and then out to the basin. The motor, as far as the motor sits on the outside of this tower, we have here's a picture of it right here, and they also have like a little jib crane on the top of it where you can put a chain fall hoist if the motor has to be removed. As far as draining it, like I said, each one of them, each individual tower can be shut off and the other one drained for service. As far as the operation, the bearings every 1,000 hours, 3 months to be greased. They're pillar block bearings. And as far as the safety cutoffs, we have low water cutoffs in the basin. There's nothing electronic, and we have manual floats, brass floats, plastic floats with the brass fill, pretty standard. There's nothing else there. The low water cutoff for the basin heater, and it's either 4 to 6 kW heater. I'm not exactly sure. Both of them they operate the same, and of course they have a low water cutoff in that. So that's pretty much it. I mean, I don't know. Is there any questions? Or?
I'm gonna pull up that maintenance checklist.
Yeah, we
Maybe,
can.
Might be something you can go ahead and just speak to it while I'm getting there if you want, but there's some recommended maintenance every so often that is in the O&M data that we provided the owner. So it'd be good to,
Well, it's just a month, well, I guess a monthly checklist. If you guys have somebody that goes around and does that, I mean, as far as checking things off, belts, I mean, they ask that you check the belts monthly, of course. I mean, I'm sure they do a lot more of that when the temperature's 100 degrees outside.
Is this particular one got a one-piece belt or is it?
It's a one-piece belt. It's a one-piece belt on there. And all the pulleys inside of it, they're aluminum. Yeah. So, and to remove those, you got to remove the drift eliminators on the top to get down in it. So,
What about the recommended water level on the interior of the tower? Is it identified or is it just?
it's right below where the overflow goes out to, where it starts. Of course, it takes more when it starts, then comes in where we had it, where it would keep overflowing.
So right now, we are overflowing.
We are?
We are.
Well, we'll have to check the level on the floats then, yeah.
so this checklist here is just something that's provided in the O&M documents. There's monthly, quarterly, annually recommended inspection, maintenance items to check, so.
It's a good maintenance tool. I mean, it's something to go by.
When, Mike, for the next phase of this project, we are going to get into demolition phase. So that now, we'll be doing demolition very close to those towers, right? What, I guess what do we need to worry about then? I mean, I'm concerned that as those towers are running, that whatever's getting kicked up into the air is going to.
We usually have to take them out the intake louvers and power wash them. If they're that bad, or put some light cleaning chemical on them, sometimes you can get away with just hosing them off, depending on what it is.
I'm Desmond Glover with Colonial Web again. Right now we're going over exhaust fans throughout the building. We have 26 exhaust fans on the roof. All of them pretty much are the same direct drive centrifugal exhaust fans. You have three exhaust fans on the roof that are belt driven. That would be your kitchen exhaust, your refrigerant monitor exhaust fan, and also your dishwasher exhaust fan. The rest are pretty much maintenance free, direct drive. They all have speed controllers. They're controlled by line voltage thermostats, which are set at about, I think they're 78 degrees on the, specifically for like the data closets or whatever. So once your set point gets above 78 degrees, then your fans kick on. Any questions on?
Are there any safety interlocks that we have to be concerned about in the event of a fire or anything like that we have to be reset so we could initiate the fans to be back on?
As far as tied into BAS? Or
Well, I mean,
they all have backdraft dampers on them.
so they have fire dampers on them.
Yes.
But as far as any electrical,
Building,
that's like a smoke detector or anything like that, none of that stuff's in line with none of the exhaust fans that you know of? I mean,
no, sir.
Okay, good afternoon. My name is Trey Harmon. I'm with Captive Air Systems. We supplied the indirect fired heated makeup air unit for the hood system that was shown previously. First things first is the filtration for these units. You're going to want to check these 2 to 3 times a year. We tell most schools just to do it at the beginning and end of each semester. These can be washed. Be careful with a pressure washer. If it's too much pressure, it will knock out the mesh, if you will. It can loosen this material. Other than that, a light spray with a degreasing formula and they go in very simply. Now we're going to take a look at the controls side of this unit, and I'll join you there. Okay, besides the filtration, the only real basic part of maintenance for these units is to come up again twice to 3 times a year, and you're going to check your belt tension. You should have between a 1/2 to 3/4 inch of play on the belt on both sides. This belt has excellent tension as it is. That should be excellent. You're going to look for any type of rubber shavings at the base of the unit. What you're looking for is uneven wear in your belt. That could cite that there was an issue with the pulleys not being properly aligned, but as is, everything looks outstanding. Further back are the controls for this heater. First, we have the intake air thermostat. This is what tells us how cold or what does the temperature need to be outside before I try to turn on. In this case, it's set for 60 degrees Fahrenheit. So if the outside air temperature is 62 and the kitchen staff says, hey, I feel cool air coming in, it's because it's delivering 62-degree air. It's not going to fire the heater until it drops below 60 degrees. On the opposite end of the unit is our discharge air thermostat, currently set at 70 degrees. So that means that whether or not it's 55 degrees outside or 35 degrees outside, the discharge air temperature will be 70 degrees on this unit. So again, for maintenance, it's 2 to 3 times a year with filter cleaning and checking your belts. And for comfort control for your staff, you may need to access the discharge air thermostat.
Are they greasable, little rod bearings on that?
The answer to that question is yes, and they are accessible through a grease nipple on the outside of the bearing. You'd have to get real tight to get that shot.
Should be a bearing on the opposite side.
Correct. And there is opposite side access through the same panels on the other side.
And you said the 60 degrees there, that's outdoor ambient temperature, but then your supply is 70, correct?
Correct.
And that's, I guess 70 is going to be the maximum period that you would ever see in the space? Is that what you're saying?
Coming from our supply plenum, that's correct. And it will not turn on. This is basically telling it how cold does it need to be before I turn on.
Okay, this is kitchen exhaust fan 1, what we're looking at now, which is tied into the captive air kitchen exhaust, which is also tied into the makeup air system. What you have here is a 3-phase, 3 horsepower, 460 volt motor that comes on in conjunction with your exhaust hood from your kitchen exhaust. It's belt driven. You also have pillar blocks that can be greased. You want to check your belt tensioning probably every quarter. You also have a grease interceptor here on the side, which should be checked monthly. This, as the supply air fan, has a frequency drive that's in the exhaust hood down in the kitchen area that should be turned off before killing main power to the unit. And what we're talking about now is your hydronic pump packaging system, which consists of a lead lag, condenser pumps, primary chill water pumps, secondary chill water pumps, and hot water pumps. Each pump has its own ABB drive. They're set to run in a lead lag sequence. Each pump has a discharge pressure gauge on the outer side of the pump and a suction side gauge on the front side of the pump. Your condenser water pumps controls the water going and coming through the cooling towers, which goes through your chiller condenser barrels. Your primary chill water pump are the pumps that's going to circulate your chill water between the chiller through the pumps. Your secondary chill water pumps pump your chill water, your 44-degree chill water, to your air handlers for air distribution. Your hot water pumps are your pumps coming off of your boiler loop, which is then pumped into your air handlers, and your heaters and your VAVs. Okay, strainers. I want to get into, this is a bucket strainer coming off of your cooling tower loop. I want to get into how you would clean it and when you would clean it. Basically what you would do, you would shut your valve off, you would kill water flow going through this valve. You would then attach a hose to your ball valve, empty your water out, take these bolts out here, and there's a basket in there that what you take out and clean. And this is normally done annually.
All right, this is one of our cells on our Vapco cooling towers. This is our basin heater right here, a basin heater control. This is our thermostat for our basin heater, our sensing bulb, our low water cutoff, and this is the actual heater in the basin heater right here. This is the intake louvers for it. As you can see, they go all the way around. All right, these two top pipes are your supply pipe into each cell, cooling tower cell. Goes in the top, actually flows down where air comes in the side and is taken out the top. This is the return piping right here from the bottom of the basin on both towers. This is the equalizer line hooked together. It goes out. This is your overflow piping right here, and this is also your drain piping. This copper line right here going to each cell goes to the mechanical float in each one of the towers. This is the external motor for the cooling tower right here that's belt driven. To the left of the motor is the access door where you can get in there, of course. And to the right of the motor is the little crane that comes around. If you ever have to take the motor down, that's where you make your adjustments to tighten the belt on the motor.